Thank you.
Now recording. Yeah. Okay, so for number 8, for the practice test for final, it says let R squared have the weighted Euclidean inner product 3u1 v1 plus 5u2 v2, and let u equal that vector, v equal that one, w equal that one, and k equals 7. Compute the stated quantities. So for A, we want to find the inner product of k, v, and w. Okay, so maybe I might just try to write on here because moving this. Actually, I don't like that. Let me. Maybe I can. I know what I'll do. Oh, sorry, give me 1 second. Get these buttons working. Doesn't let me. Oh, I know what I can do. No, I can't do that. Okay, so what I'm going to do is I'm going to type in this stuff on Word. Okay, I just need to create a new file. Give me 1 second. Okay, so this is. Oh, wait. Oh, now I know it. Now I know it. Just, we already started this lesson earlier, right? So I can. Okay. Now I got it. Okay, so we're on Word. And so we're going to look at number 8. So we're going to let R2 have the weighted Euclidean inner product. Where the Euclidean inner product is defined as being u comma v, which is equal to 3u1 v1 plus 5u2 v2. Okay, and so u is going to equal a particular vector, v is going to equal 4 comma 1, w is equal to 0 comma negative 1, and then k is equal to 7, and u is 2 comma 2. Because this is computational, but it's kind of good to start to maybe an easier one to start off with. So kv comma w, we want to calculate in A. In B, it's the norm of u. B, it's the norm of u. C, it's the distance between u and w. And in D, it's the inner product of u plus v comma w. Okay, I now have the question written down, so I can now start doing something. Okay, so so this is equal to, so when you calculate this, k is 7, so this is 7 times v, where v is 4 comma 1, and then the inner product of that with w, which is 0 comma negative 1. Okay, well, this is equal to, sorry. Okay, so you see how I have the k, which is 7 here, u, v, which is here, and the w, which is there. So right now I just plugged in the values of those things. So 7 times 4 comma 1, just what it would normally be, which is 28 comma 7. And then you take the inner product of that with 0 comma negative 1, right? And this inner product is defined by this weighted Euclidean inner product. The first weight is 3 and the second weight is 5. So to compute this, you just take 3 times the first component of the first vector times this first component of the second vector, then plus 5 times the second component of the first vector times the second component of the second vector. The first term is 0 plus, and then, well, minus 35. This equals negative 35. Okay, so that makes sense. So that's how you compute the inner product of those two of this using that Euclidean, that weighted inner product. So now the norm of u is equal to the square root of the inner product of the vector u with itself. And so that means that this is equal to the square root of the inner product of u, which is 2, 2, with itself, which is 2, 2. And so that's equal to the square root of, well, the first weight is 3 times 2 times 2 plus 5 times 2 times 2. And so this is equal to the square root of 12 plus 20. And so this is equal to the square root of 32. And this is equal to the square root of 2 times the square root of 16. And that's equal to, the square root of 16 is 4, so I just rearranged it. So it's 4 root 2. So the length of u with respect to this inner product, the weighted Euclidean product here, the norm of vector u with that inner product function is 4 root 2. And then the distance between u and w is equal to the norm of u minus w. And that's equal to the square root of the inner product of u minus w with itself, u minus w. And so this is equal to the square root of, well, the first, so actually let's do u minus w. U is 2, 2, minus w, which is 0, negative 1. And then it's comma the same thing, u minus w. So it's 2, 2, minus 0, negative 1. And so, okay, so that's equal to now the square root of the inner product. Well, 2, 2 minus 0, negative 1 is 2, 3. And so that's the inner product, 2, 3 with itself. So this is the square root of, the first weight is 3. So it's 3 times 2 times 2, plus the other weight is 5 times 3 times 3. And this is equal to the square root. Well, so the first thing is 12 plus 45. So that's equal to the square root of 57. Okay, so that's the distance between vectors u and w by computation. And this is equal to the inner product of u plus v, which is 2, 2, plus v, which is 4, 1, w, which is 0, negative. And so this is equal to now, so 2, 2 plus 4, 1 is 6, 3. This is 0, negative 1. So you're taking the inner product of those two things. The first weight is 3, so it's 3 times 6 times 0, plus 5 times 3 times negative 1. And that's equal to 0 minus 15. That equals negative 15. Okay, so that's A, B, C, D for number 8. Anyone have any questions about number 8? Okay, good. Okay, so that's number 8 on the review sheet. There's a bunch of the problems, so I don't want to do something that's like really long. Let's see number 10. Determine whether T is a matrix transformation. Justify your answer. Okay, so a matrix transformation, a matrix transformation is a linear transformation, and a linear transformation is a matrix transformation. So if you can show that this map T is linear, then it's a matrix transformation. Okay, so determine whether T is a matrix transformation. T of x comma y is equal to that. So T of x comma y is equal to 2x minus 3y comma x minus y. Determine whether T is a matrix transformation. Okay, so this is number 10. So determine whether T is a matrix transformation. Okay, and here T of x comma y is equal to 2x minus 3y comma x minus y. Okay, so a matrix transformation is a linear transformation. And a linear transformation is a matrix transformation. So if we show that T above is a linear transformation, then by the above fact, it is also a matrix transformation. Make sense? So to show that capital T is a linear transformation, we need to show two things. The first thing we need to show is that T of x plus y is equal to T of, so instead of, let me go u plus v. T of u plus v is equal to T of u plus T of v. And this is for every u and v in the space. The second thing you need to show is that T of k u, where u is your vector, is equal to k times T of u. K is a constant. This is for any vector u in your vector space and for any constant k, real number k. Okay, so let's show each. So below each of them, we're going to show each of them. So if you take T of u plus v, right? And let's say that u is equal to the vector x comma y, and v is equal to the vector x prime comma y prime. Okay, then T of u plus v is equal to T of, well, it's x comma y, which is the first vector, plus x prime comma y prime, which is the second one. This is equal to T of the ordered pair x plus x prime comma y plus y prime. And so this is equal to, well, the first component is x plus x prime. And so the formula for T tells you that this is equal to an ordered pair where it's 2 times the first component, which is x plus x prime, and then minus 3 times the second component, which is y plus y prime. And so that whole thing is the first component of the image. The second component of the image is going to be the x coordinate, which is x plus x prime, minus the y component, which is y plus y prime. So that whole thing is the image of T plus T of u plus v. Now, T of u plus T of v is equal to, well, T of u is 2 times the first component of u, which is x, minus 3 times the second component of u, which is y, comma x, the first component, minus y, the second component, right? So that matches with what's up there. This is plus T of v, where T of v is equal to 2 times the first component, which is x prime, minus 3 times the second component, which is y prime, comma the first component minus the second component. So that's T of U plus T of B. And so maybe we can express T of U plus B in that way. So if we combine all like terms, we get 2x plus 2x prime minus 3y minus 3y prime, comma, here we have and so here we just have x plus x prime minus y prime. Okay, so here I'm going to write this out. So I'm going to add the first terms and second terms. So you have 2x plus 2x prime minus 3y prime, comma, the second term is x plus, I'm going to move the terms around, x plus x prime minus, in parentheses, y plus y prime. Okay, so you can write it like that because you have a minus y here and you're adding a minus y prime here. So that's the negative of y plus y prime. Actually, I don't need this here. So now I've expressed T of U plus T of V in this way. And you could go either direction here. So let's say we continue in this. So this is equal to, now, this is equal to 2x plus 2x prime minus 3y minus 3y prime, comma, x plus x prime minus y plus y prime. Okay, so this thing is this. And so that means that this is equal to T of U plus T of V. And so that shows the first property of a linear transformation holds that T of U plus V is equal to T of U plus T. And then the second property is that T of KU equals K times T of U. Well, T of KU is equal to T of K times what U is. U is X comma Y. So this is K times X comma Y. And so this is equal to T of Kx comma Ky. And this is equal to, so T is defined to be the map. I'm going to remind us what T is by copying it and pasting it here. So reminder, that's T. So T of Kx comma Ky. Okay, T of Kx comma Ky is equal to the ordered pair where the first it's 2 times the first component, which is Kx, and then minus 3 times the second component, which is Ky, comma, the first component, which is Kx, minus the second component, which is Ky. And this is equal to the ordered pair where you have, we want to factor out the K. So you can think of this as K times 2x minus 3y, comma, K times x minus y. Okay, so just factored out the K in the first and second coordinate. And now I can move that K out. This is K times 2x minus 3y, comma, x minus y. Okay, and that is T of X comma Y. And so this is equal to K times T of X comma Y. Okay, so T of KU is equal to K times T of X comma Y, but that's K of X comma Y is U. This is K times that. So you get that. So T of KU is equal to K times T of U. And also reminding you that U is equal to X comma Y. Okay, so those are the two properties. So what we just showed is that T is a linear transformation, which implies it's a matrix transformation, and you're done. So that's number 10. That's the number of the problem. These are the two properties of a linear transformation that's satisfied by T. Okay, so number 10 is also good. Okay, it's kind of late, so I feel like maybe this should stop here. I don't want to torture all of you. So maybe we'll stop there unless anyone has questions. Anyone have a question about anything that you want me to go over? Or that's good. Okay, so I'm assuming that's good.
So just to confirm, when's the test again and like what time?
Okay, so the final is, I think it's, did I write it down? Okay, so I'll write it down here for you. So Math 241 final. Okay, so this is a reminder. Okay, so Math
231.
All right, Math, thank you. Math 231 final is on 12/21/2021, and it's from 8:30 p.m. to 10:30 p.m.
Also, Professor, quick question. So during our finals, it's going to be also like 5 problems or more than that?
No, so it's going to be more problems than the other exams, right? You can think of it as looking similar to this exam for the practice exam here.
Okay.
So imagine it's modeled like this, like a lot like that. Okay, so okay, so send. I'm going to remember. I said this before, right? So I'm going to send the Zoom link the day before the exam on 12/20/2021. Okay, to your email accounts associated with Blackboard. I don't know how else to say that. Okay, so that's it. So is there anything else you need to know about the final?
So do you recommend studying like just that review sheet or like everything?
So I would suggest the first thing you do, I guess, study the review sheet, right? Try to do the problems in the review sheet. Then I would say if there's topics you don't, so we covered a lot, right? So you should know the Graham-Schmidt process, right? You should know how to orthogonally diagonalize a matrix. You should know how to, am I saying this fast? You should know how to find the eigenvalues of a matrix, right? You should know how to find the eigenspaces corresponding to eigenvalues. You should be able to find bases for each of the eigenspaces. You know, algebraic multiplicity for each eigenvalue, geometric multiplicity for each eigenvalue. You should know, maybe the transformation matrices. So like if you're given a point and you're said what happens to the point after you rotate it about the origin, certain theta number of degrees, 30 degrees or something. It's an easy problem. You just multiply them up by a matrix, but you have to know what those matrices are. And that could be a problem. So I suggest you study that so you're prepared for that. And there's other things too, but those are some things. You should know the equivalence theorem, right? There's a lot of parts, but all the parts are very similar, right? Yeah, I want you to understand the equivalence theorem, right? If you understand the equivalence theorem, then remembering all the parts is really just understanding the theory, which means that you know when you have in a sense, one of those things happening. At least in the first few forms of the equivalence theorem, you have a few statements in the beginning, like A, B, C, and D. You should definitely know all 4 of those, right? And then there's a lot of other ones, and if you know them, that's great. But you should definitely at least know the first few, okay? But that's important. That equivalence theorem is very important. You should know that. Yeah, and there's other things too. I'm not saying everything there, but those are some of the things you should know. Okay. Anything else you want to ask before I go? Anyone? Okay, you're welcome. Thank you for staying for the review. I want all of you to do well. So I'm glad that you stayed and that you are trying to do well.
Professor, thank you for having us. Thank you.
You're welcome. Good night.
Good night.
It's over.
Thank you, Professor. Good night.
Good night. Thank you, Erkan, for coming to office hour all this time.
Yeah. So this is gonna be on YouTube, right?
Yeah. It'll take me a little while to organize this and put it on, but once I figure out how to get all this, it'll be up. Yeah, on Blackboard and YouTube the normal way.
Okay. Thank you. Good night.
You're welcome. Good night.